They're going to be true, false. I'm going to assume that, okay, I'll write them, but then that's okay. You can read them? Okay. Problem number 29. These are just statements. They're either true or they're false. The first statement is, it is impossible to lick your own elbows. That is true. Although, let me hear that.
Yes.
Let me explain to you the purpose of that question. So this is the reason I put a question like that. If I do put a question like that on the test early on the first page, so everybody can lighten up. If you answer it wrong, you'll get credit. That question is neutral on the test.
But that's not true.
There are people, you're right.
Actually, that's my cousin, and he did it to me right in front.
Yeah, there are people in this world who can lick their elbows. But the reason I asked this question, if you look on question number 33 on the next page, which is strategically located on the next page, it says, you tried to lick your elbows, didn't you? Because I've asked this question, and it's just sort of a joke to lighten everybody up. You'll do much better on the test if you relax. And that was the objective. So don't worry about it. I don't care what answer you put, but I'm glad to hear your input. And I have had that feedback over the years. It says, oh, by the way, because there are enough people who have met somebody who can lick their elbows, but I've tried. And I've actually seen a room full of people the first time I asked them. So I could tell when they were at that part of the test. Okay, so that one doesn't matter what you put, true or false, whatever you like. That was just there for a joke. It's not a chemistry question. But out of the 55 questions, there are 2 that aren't chemistry. Okay? So that was for fun. Okay, number 30. Metals form basic oxides. Is that true?
True, yes.
Absolutely. That's one of their defining characteristics of a metal. Number 31. There is a preferred degree of freedom in every sample. Is that true or false?
False.
That is absolutely false. If that was true, then, like for example, could I see this as a sample for a second? See the gas contained in this? If there was a preferred degree of freedom, then the kinetic energy would not be. What is the principle I'm talking about here? The principle of what of energy? There's a word for it. It was in the fundamental definitions. Equipartition of energy. What that states is the energy is partitioned equally to all of the degrees of freedom available. If it was not so, let's say that the kinetic energy in this direction was preferred, and it got all the kinetic energy, and the rest of the kinetic energy was not distributed in any of the other 2 of the 3 possible directions that I can decompose it to. What would happen? They would all bang into this side and it'd start to fly. Let's even better. Let's say they're all going up. Then it'd be Wingardium Leviosa. Okay. And trust me, if you guys you start to experience things levitating and floating around, let me know. But other than that, this is a simple observation that is consistent with the kinetic energy in a system of molecules is distributed equally to each of the 3 translational degrees of freedom available to the molecules in the system. There's no preferred degree of freedom. That kinetic energy is just one of the degrees of freedom, and there's a degree of freedom for every type of energy. So we can have vibrational energy, rotational energy, etc., etc. The equipartition of energy says that energy is distributed equally to each of the degrees of freedom. And that's a concept we want to have straight up in our foundation on day 1 for this class. It's going to really be very important on the last day of Chemistry 1B 9 months from now. I'm not kidding. This is something that will be very important on your final in Chemistry 1B. and also part of your foundation for everything you do from now on. If you go on to study quantum electrodynamics, we'll be talking about degrees of freedom. Okay? So, this is a good foundation concept. Now, did you have a question back there? What? You forgot it? I'm sorry, I talk too much, don't I? Okay, let's move on to the next one. Number 32. This one's much easier. Liquids have a fixed shape.
False.
No, that's false. Absolutely false. What, do they have a fixed volume? Yeah. But no fixed shape. Okay, that would be a solid that has a fixed shape. Okay, number 33, we've already discussed. You tried to lick your elbows, didn't you? That was part of the joke. Okay. Number 34. The significant figure convention applies to all measured quantities used in a calculation. That is absolutely true. We've even discussed that already on the previous parts of this session. Now, number 35. Your weight depends on where you are. That is absolutely true, because your weight is the force that gravity exerts upon you in a gravitational force field, and that is due to your position in that force field. So you weigh less, I believe you weigh less at the equator than you do at the North Pole. And you certainly weigh much less in orbit. You're weightless in orbit. You weigh less on the moon than you do here on Earth. Yes?
So if you went about 100 pounds on the equator, how much would it be then? Like, are we talking about like a little bit, like slightly off?
A bit, very, very, very slight.
Okay.
It's not that significant, but it is significant. Like what the force you would exert here is different than the force you would exert on the moon. In other words, and that would be evident by if you sprang up with this much force. Here I only go up this high. If I did the same thing on the moon, I'd probably go up this high. Because it's a much smaller mass, the moon. So its gravitational constant, or its mass in the gravitational equation, the force equation, is much smaller. Okay. Now, and that's the difference between weight and mass. Your mass doesn't change. It's an invariant quality. It's an invariant quality of matter, a physical property of matter that creates and responds to a gravitational field, and it doesn't vary. Your weight is the force exerted on a mass, or the weight is the force exerted on a mass in a gravitational field. Okay. 36. Non-metals form non-conductive brittle solids. Is that true? Yes. Whenever we get a non-metal, it is indeed they're characterized by, generally as a rule, they are non-conductive, and generally as a rule, they are brittle. Okay. Not all non-metals are solids. Some of them are gases, some of them are liquids. But those that form solids are generally brittle, and they don't conduct electricity. The exception would be carbon in the graphite form, not the diamond form. Okay? So, where are we now? Oh, okay. Number 37. Metals readily form compounds with non-metals. Is that true? Absolutely. Okay? One of the defining characteristics. Number 38. The chemical identity of a compound is changed in every chemical process. Is that true? That's what we define a chemical process. Okay, chemical identity of a compound is changed in a chemical process. If it's involved in a chemical reaction, that's a chemical property. It's the chemical identity of the compound is changed. So, number 39. Solid metalloids are semiconductors of electricity. Is that true? So we had a whole slew of true questions there in that particular group. Okay, are there any questions about those questions? Yes.
There is a super degree of freedom and there is not.
Yeah.
Gravity, would you say that's also true? I mean, like not true.
Well, gravity doesn't represent a degree of freedom. A degree of freedom is for a given molecule, if it has energy, there is a corresponding degree of freedom to every degree of freedom. For example, like there are only two types of energy. What are they? Kinetic and potential. You're right, gravity does factor into that but as a potential energy, but then the potential energy is going to be due to its position in a gravitational field. So it would factor into it. But the ones we're going to be most that are going to be most relevant for our purposes is going to be something like the potential energy contained in a chemical bond. Okay, and so like if I have a diatomic molecule they're bound together covalently, they can go chucky, 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 chucky. They can vibrate. Okay, that's going to have a kinetic energy component, and it's going to have a potential energy component. And the point of equipartition of energy is that the kinetic energy is going to get the same amount of the energy available to the molecule as the potential energy. So it's going to have 1/2, turns out 1/2 kT for the kinetic and 1/2 kT for the potential. So kT overall is stored up in every vibrational degree of freedom. And so when I talk about that, equipartition of energy just says the energy is shared equally for every degree of freedom. Okay. And it's a concept we'll be dealing with all semester. Okay. Now, are there any other questions about this part before? Yes? I can't understand you. Speak louder.
When you talk about that diatomic molecule, it has kinetic and potential electrons, which is electrics.
It has kinetic and potential and what?
Kinetic and potential,
It's okay, don't need to focus.
and it balances out in the x-ray direction, and then with gravity, you might not know.
Well, it doesn't. Well, it depends on where it's how it's oriented, and it's tumbling around. The gravitational potential energy is going to be negligible in this. What it means is there's not going to be any preferred degree of freedom. So the energy stored up is going to be the same, and actually it's going to have more than enough probable kinetic energy to overcome the gravitational attraction and keep it from falling down. If it bounces into the earth, it's going to bounce right back up. And that's where, when we start talking about the various states of matter, for example, with the gas phase, the kinetic energy is greater, much greater than the attractive energy between molecules, and that's why they're in the gas. In the liquid phase, the kinetic energy is about the same magnitude as the attractive interactions, and that's for they're free to move about, but they're still bound into the liquid. And when we get to the solid phase, the kinetic energy is much less than the attractive forces, and so it's a solid. But that's a bit different than the equipartition of energy. And the equipartition of energy just says there is no preferred degree of freedom. For every molecule, there's no one degree of freedom that gets more of the energy available than any other degree of freedom. So the kinetic energy is the same in all possible directions. The average kinetic energy is going to be the same. Does that answer the question? Okay. Any other questions? Okay. Then what we're doing here, now we stop it and start it again. Okay, so stop it.